So what were we doing? Last time we were talking about heat exchangers just in general terms and coming up with approximate models. What we ended up with was this control volume analysis where we're trying to look at a counterflow heat exchanger. Right? Counterflow, it's important that we're considering counterflow versus parallel flow. So counterflow, the cold is going this way, hot is going this way, and you have this coupled control volume. And it is coupled both in the location, x, but also in the differential heat that's going from one fluid to another fluid. So we have to consider both of them at the same time. If we do this, we go through, you can do the same analysis we always do. You expand it out, and we get this expression where we say the amount of heat that I transfer, dq dot, has to be equal to the capacitance rate, C dot, on the hot side, times dTh dx dx. I gave you this, you could do the same thing on the cold stream, and you end up with basically the exact same equation, right? dq dot is equal to minus C dot C dTc dx. And remember, dTh and dTc, or TH and TC, are different temperatures. They're independent of each other, but they're coupled by these equations. So one maybe confusion here is dq dot's going this way. So why do I end up with a negative sign and a negative sign? Shouldn't it be flipped around? Well, think about it for a second, right? You have one where the flow is going this way and heat is leaving. In the other case, flow is going this way and heat is entering. So you kind of get this canceling of negatives, and you end up with the same thing. And actually, if you think about it further and you look at this, we're looking at the temperature gradient in the positive x direction. So this being a counterflow heat exchanger, what is the temperature gradient in the positive x direction? Okay, as you're going to have a temperature gradient in the positive x direction. They're both kind of doing the same thing. They're moving like this together. So the gradients are the same in both flows. If it was a parallel flow condition, the sign would be flipped here because one would be decreasing while the other is increasing. Right? Make sense? Okay. So this is where we left it. This isn't enough for us to be doing model development with it yet. So let's continue and take this further to look at actually how do we compute temperatures and stuff with this. OK, so let's write back what we have, our differential equations at the top here. We said dq dot is equal to minus C dot H dTh dx dx. That's for the hot flow. For the cold flow, we have dq dot minus C dot C dTc dx dx. So what do we need? I guess we need this missing relationship is what is this q dot, or how do we express q dot? Well, I guess we could look at the actual resistance between the flow streams here. Like if you look back here, we could come up with an expression for q dot that relates the temperature here, I guess TH, to the temperature here, TC, at this given position x, given the geometry that's in here. Or we already talked about that idea of the whole resistance network that exists between these two fluids. So we can develop a model for q dot based on the actual heat transfer network that's involved here. In general terms, I guess what we're saying is I can have a third equation that's dq dot is equal to TH minus TC. Those are both at the position x that we want to evaluate, divided by the resistance. So the resistance would be R total. But let's think about what that resistance actually is. So R total, if we define that to be the total resistance for the entire length of the heat exchanger, we have to adjust that for the fact that this is a control volume. So it's dq dot. So we're looking at just a differential element. So how do we scale R total to account for the fact that we're just looking at a single differential element? Well, it would be, I guess, the ratio of dx over L, right? dx over L is going to scale that for us. But the question is which way, right? Dx over L or L over dx. So R total, if we take a differentially small element, is the resistance going to go up or down? Up, right? Smaller area means higher resistance. So we'd better take L over dx. So R total times L over dx, where L is the total length of the heat exchanger. That's the resistance associated with this single differential control volume. OK, so that's another way of saying dq dot is equal to th minus tc. Remember, 1 over R total was our conductance, UA. So we can just make that substitution. Let's call that UA times dx. So this is an independent equation from the ones on the top. Now we have 3 equations, right? 1, 2, 3. I can probably take this further and get rid of the differentials and actually have expressions here. So let's do that. Bringing this stuff together. So we're going to substitute dq for the new expression that we have. Yeah, go ahead.
Get rid of the L.
I didn't mean to do that. dq dx. Thank you. I wished it away, and it went away. It's there. OK. So L is there. Thank you. OK, so we're going to now use this dq dot, substitute that then for the equations on the top, and it just becomes UA times TH minus TC times dx over L equals minus C dot. Let's take the hot one first, so C dot H times dTH dx dx. Do the same thing for the cold. I'll just write that out. So we have it, UA TH minus TC dx over L equals minus C dot C dTC dx dx. OK, so we have a differential equation. We have 2 differential equations in terms of temperature. Q dot no longer appears. Good, so two differential equations, TH here, TC here, TC here. We have dx's. Now the challenge is just to solve this. Right? It's not really a challenge. It's fairly straightforward. So we can solve this. I guess we could rewrite it if we wanted to be careful. Let's just rewrite it like this. So we would write it in standard form as dTH dx equals minus UA over L C dot H times TH minus TC. And then the other one is dTC dx equals minus UA over L C dot C TH minus TC. The other thing we want to do, though, is we know that, OK, this is a first order derivative. So we're going to need some boundary conditions to go with this in order to solve it and pin it down. So let's say what our boundary conditions are on the 2 flow streams. So the boundary condition on the hot side, that could be, I guess, a couple things. Typically, what you're going to know is the hot temperature coming in. If you're trying to predict the performance of a heat exchanger, usually you know what you're giving to the heat exchanger. So let's have a boundary condition that relates to the hot temperature coming in. So for our heat exchanger, we'll see the boundary condition would be TH at x equals 0. I'm going to flip back here so we can look at it. So we are saying hot is coming in here at x equals 0. Cold is coming in at x equals L. So we have to have our boundary conditions considering that. So at x equals 0, that's equal to TH in. And then down here we have TC at x equals L is equal to TC in. So this is, I guess, our, this thing down here. That's our mathematical statement of the problem in terms of temperature, right? The ODEs and the boundary conditions. So we can solve this, right? We can solve this. To solve this, I guess, you could do like a coupled solution. Another thing you could do is you could actually combine these two by saying, I'm gonna take this side, subtract the left-hand side, subtract the right-hand side from each other, and you can combine them together. So if we did that, we would get this equation up here, which is d t h minus tc dx is equal to minus ua over L th minus tc times 1 over c dot c minus 1 over, c dot h. I'll do that again. 1 over c dot h minus 1 over c dot c. So that's just subtracting the two. Why would I do that? Well, I guess I can now make a substitution. I can make a substitution that says theta is equal to th minus tc. Express this in terms of theta, which is d theta dx equals minus ua over L times theta times 1 over c dot h minus 1 over c dot c. Now I can just solve this for theta. Right? That's easy to do. So separate and integrate, we would get, let's see, I'm going to just rearrange this. So d theta, I'm going to bring the dx over to the right side, dx over here. I'm going to bring theta over here. So now I can integrate this on both sides. Integrate this on both sides. So I'm going to integrate from from theta from x equals 0 to L. And I'm going to integrate x from x equals 0 to L. And if I do that, then I get the integral of 1 over theta is log. So then log of L minus log of 0, or log of theta at L minus log of theta at 0 is the same thing as the ratio of those two. Right? So you could use say it like this. So log of theta at x equals L divided by theta at x equals 0. That's equal to then the minus ua times 1 over c dot h minus 1 over c dot c. So the L went away because of the integral of x. Finally, we got rid of L. Okay, so this is the expression. Again, what is this telling me? This is a relationship based on the geometry of the system, right? The geometry is here, UA, between temperature and the flows. This is my third equation that I need to solve the problem. Two energy balances in this. Let's take it and get it back to temperatures just so you have that available. So make that reverse substitution. Then the final equation would be ln of th out minus t c in over th in minus t c out. That's equal to minus ua times this 1 over c dot h minus 1 over c dot c. C dot c. All right, so that's kind of your final solution there. And what is this? This is for counterflow only. So if I give you a parallel flow, this is not right. Right? This is for our situation with the boundary conditions, with the ODE that we developed for a counterflow heat exchanger. I'm going to write that so you don't forget it. This is for counterflow.